Hello to everybody, dear colleagues. Good morning, good afternoon, good evening, good night. Today it's a pleasure for me to present, we have Vladimir Dotsenko from Strasbourg University, yes?
Yes.
And he will speak on Diamond Lemma and Maurer-Cartan Equation. Please, Vladimir, you can start.
Thank you very much. Thank you for the invitation. It's normally I would much prefer to make it to Brazil to give such a talk in person, but now we do what we can do. I am absolutely really excited to see on the list of people attending many names that I know, many people whom I haven't seen for a very long time. So at least it gives us an opportunity to meet in some way. So maybe it's not all terrible. So I will talk. So you can see my blackboard, right? The thing I'm writing on. Yeah, great. So I'll talk about a recent work, joint work with my student Pedro Tamaroff, who is about to defend his thesis in about a month and a half. We put it on the archive last year. This is the archive identifier, and somehow it's related to the main theme of this seminar in some marginal way, because the main motivation for us was to understand some things about associative algebras, not about Lie or Jordan, but however, one of the formulations, the formulation that of our vision of the story that I like a lot is done in terms of the Maurer-Cartan equation in differential graded Lie algebras. So there is some Lie theory, of course, as it almost always is. But in any case, my minimalistic goal would be to just explain to you the key words in the title of the talk. So I will briefly remind you what the diamond lemma or composition-diamond lemma is, and then I will explain to you how to view this result in the context of deformation theory, in the context of homotopy theory, and how you can interpret this result in terms of the Maurer-Cartan equation in some differential graded Lie algebras, which has certain advantages. First of all, it kind of shows that the classical diamond lemma is not really one result, but there are many natural differential graded Lie algebras that you consider, and each of them gives its own diamond lemma. In a sense, I will explain to you two different versions in particular. I'll try anyway. And plus, it gives some idea how to generalize this result to other algebraic structures, not necessarily associative algebras, but, well, whatever algebras you wish, in which you can do some version of writing theory. I'll try to touch that topic towards the end. But in any case, the diamond lemma, or as some people say, composition diamond lemma, concerns normal forms in algebras. And normal forms is something which is will be understood in some relatively precise way. So algebras, I will put in quotation marks because you can put, you can have many different situations here. So somehow historically results like that appeared for when studying normal forms in various contexts related to mathematical logic. So there are famous works of Church and Rosser, which were followed by the Diamond Lemma of Newman in 1940s. So this happened in 1940s. Then somehow there was a there were some groundbreaking contributions of Shirshov in the algebraic context, precisely in 1950s and 1960s. Then somehow in 1960s there were works of Buchberger, who introduced the thing widely known as Gröbner basis, which made this story perhaps particularly famous because it, besides proving some theoretical results, so his motivation was about solving systems of polynomial equations, which of course is very attractive for applications. So this is 1960s. Then somehow later on there were works of Leonid Bokut and George Bergman. And many. So this list is not trying to be complete. Is some little milestones of things which are related to this theme of composition-diamond lemma, and in general, so I'm going to discuss the version of this thing for non-commutative but associative algebras. So this is essentially the context of work of Bokut and Bergman, which was also implicitly present in work of Shirshov on Lie algebras, because somehow, in some sense, one can interpret some of Shirshov's work as doing things inside the universal envelope of the algebra, I suppose. But in any case, so what I'm going to, so the most of the algebras today for me will be non-commutative associative algebras. And studying normal forms means that we work with non-commutative associative algebras presented by generators and relations. And now let me give you a very naive example, just to somehow illustrate the whole point of normal forms. I apologize for simplicity of this example. I'm sure that the majority of people attending this talk know quite a bit of what I'm talking about much better than I do. But so let me give you examples. Actually, I'll give you 3 very similar examples. Even 4 perhaps. So let's take the free associative algebra with 2 generators, x and y. And I'm going to define four different quotients of this algebra. I'm going to take the quotient by the ideal generated by the element xy minus yx. I'm going to take the quotient by the ideal generated by the element xy minus yx minus y. I'm going to take the quotient by the ideal generated by the element xy minus yx minus 1. And finally, I'm going to take the quotient by the ideal generated by the element xy. Somehow, you see, four examples are kind of similar. You always take the quotient by one element, and the element sort of has starts with xy, and then there are some other terms. Sometimes there are no other terms. And in principle, the first three algebras, people who work with associative algebras usually would know and like for various reasons. So this first algebra, we all know what it is. This is the algebra of commutative polynomials in x and y, which is presented in this funny way as a non-commutative algebra where commutativity is an extra relation. This algebra here, when we take the quotient by xy minus yx minus y, this is the universal envelope of the two-dimensional non-abelian Lie algebra, which is unique up to isomorphism. So somehow this kind of example brings us to commutative algebra. This example brings us sort of to Lie theory. And this last example, this algebra is isomorphic to the Weil algebra A1 of polynomial differential operators on the line. And so somehow this algebra brings us to the context of, depending of where your motivation comes from, quantum mechanics or D modules or whatever. So these algebras are all interesting in their own right and have some exciting connections to some wonderful mathematics. And the last algebra somehow is, algebraically speaking, it's the simplest possible because you take the quotient by a monomial, so it's very easy to describe basis and multiplication table. But it is perhaps I would say less interesting because somehow, yes, it has this strange relation. So it has zero divisors. It's a legitimate associative algebra, but perhaps less exciting than the three others. And this somehow brings me to the first slogan of my talk. And which is a very ambitious slogan, and I don't necessarily expect you to subscribe to it, but I would say that there are two almost disjoint sets of algebras. There are algebras which are interesting in some way, and there are algebras which are easy to work with. So interesting algebras are the first three examples that I gave. And the fourth example is an algebra which is perhaps much less interesting, but it's very easy to calculate in this algebra, for instance. So, and easy to work with, for example, for this example where we take the quotient by xy, this means that we know a monomial basis, a basis of this algebra, which are monomials not divisible by xy. We know multiplication table of basis elements. Basically, the product is of two is either a basis element to 0. Zero, of course, if after concatenation you suddenly find an occurrence of xy. Then you can, of course, you can easily do all sorts of things. You can compute some homological invariants, whatever. At this point, you will tell me, but wait, for the three other algebras that were listed, polynomials, universal enveloping, differential operators, we also know a basis. We also know multiplication table because, we can multiply polynomials, we can compose differential operators, we can do calculations in the universal envelope algebra due to Poincare-Berger-Fit theorem. So what's the point? My point is that you can do that only because there exists a bridge between algebras which are easy to work with and algebras which are interesting. So somehow, another slogan. So there are these two almost disjoint sets which are interesting algebras and easy to work with algebras. And then there is a bridge between these two clusters, and this bridge is essentially provided by the techniques like the diamond lemma. So the diamond lemma tells us how to reduce questions about interesting algebras to questions about algebras that are easy to work with. Because after all, of course, you are right that we can multiply polynomials. We know a basis in the algebra of polynomials, and we know how to multiply the basis elements. But somehow, when you multiply the basis elements, if you want to teach a computer to multiply a basis element, then the computer would need to to exchange x and y many times and rewrite the product of two basis elements into a normal form. And the normal forms in which you write are suggested by the quotient, by the monomial relation xy. So somehow this is the intuitive this intuitive slogan I tend to insist upon. And well, again, it's up to you whether to agree with this vision or not. But for me, that is what it is. Now, so in general, so when you have an algebra, which is the quotient of the free algebra generated by X, free associative algebra generated by X, by some ideal generated by some relations R, then what happens is that very often when you have a situation like that, you want to relate this algebra to a more manageable algebra, to an algebra with monomial relations. That would suggest to use some normal forms. So the first question is to find an algebra with monomial relations that would suggest normal forms for your algebra, which let me call this algebra A. How is that done? We write each relation little r in R, we write as m minus fm, where m is a monomial and fm is a linear combination of monomials. And now you interpret your relation R as a rewriting rule. Saying that M rewrites into f of n. Okay, this way you can try to create some normal forms. What would you do? If you see one of such elements M, one of the monomials that we want to rewrite, you can attempt to replace it by f of m. Okay, and in principle, you are not guaranteed that this process will ever terminate, because maybe you will write your monomial into combination of some monomials, those you want to write, and then you will rewriting, and it just never ends. Let me assume that you chose the way to direct the relations, that you chose the leading monomials in such a way that everything always terminates after finitely many steps. So I assume this rewriting rule terminating. Meaning that rewriting procedure for each monomial terminates after finitely many steps. There are two, let me mention already here that there are two situations. So this is where somehow there are two different fields of study. There is sort of the business of rewriting systems, where somehow you assume that termination like this happens. So it's very specific to the rewriting rules that you chose. So it uses some partial orders on monomials. So I won't go into more detail, but I would say that this uses partial orders on monomials, which are multiplicative in some obvious sense. And there is the formalism of what is called Gröbner-Shirshov basis, which usually uses a total multiplicative order in monomials. Except for this little difference, the two stories are doing essentially the same thing. So I am not going to distinguish them too much. I am going to focus on the diamond lemma in terms of the broader perspective. So somehow, so if we assume termination, then each element has a normal form. So, which means that it can be written as a combination of monomials that cannot be rewritten further. Right. Now, of course, what would be interesting, so this doesn't yet tell you what normal forms are, because maybe there are some linear dependencies between monomials that cannot be written further, and so you need to consider only some of them. And somehow the confluence of the property of confluence is the property of uniqueness of normal forms. Meaning that there is only one way to write every element as a combination of things that cannot be written further. Unique representation as a combination of monomials that cannot be written further. In particular, 0 has a unique representation, so this means that such monomials are linearly independent. In that case, so we have the original algebra, the interesting algebra, K of X mod R. And we have the algebra A, I call it a non-algebra with monomial relations. It's the quotient by the leading terms of relations, the monomials that we write. These guys are isomorphic as vector spaces. More precisely, each has a combinatorial basis of normal forms. And those coincide for the two algebras. And the multiplication table for basis elements, the multiplication for the algebra with monomial relations is very simple, like I was implying before. And for the interesting algebra, you deform that. You deform that by adding some lower terms. So, and the multiplication tables are related. A very simple one for the algebra with monomial relations and a deformed one for A. So what do I mean to say by that? I mean to say that for the algebra with monomial relations, the product of two basis elements is either a basis element or zero. And for the interesting algebra, you take that multiplication table and add to each product some lower terms with respect to the order to the rewriting order that you have for your rewriting. So this is the key thing to have in mind, that somehow for the following reason, there are many different ways to talk about the diamond lemma, but for me personally, my intuition comes from homotopy theory, from deformation theory, and I want to my wish is to interpret the diamond lemma in the context of deformation theory. Of course, you would note that I haven't told you exactly what the diamond lemma is. So what I will tell you now, for now, excuse me, is that the diamond lemma is a good criterion for confluence, is an efficient criterion for confluence. And I will tell you what this criterion is a little bit later. So if my talk were about Gröbner-Shirshov bases and so on, I would give you the diamond lemma right now. But since my goal is to create some connection to the Maurer-Cartan equation and deformation theory and so on, I'll postpone the diamond lemma for a bit later. And now I am going to explain to you how I want to bring deformation theory, homotopy theory into this story. So somehow what I want to, homotopical algebra suggests that another way to deal with algebras which are perhaps sometimes difficult to work with. Diamond lemma itself, as I was telling you, that slogan, it suggests that you try to replace an algebra by an algebra with monomial relations, which is simpler, and then somehow try to create a dictionary to recover results about original algebra. Homotopical algebra suggests to work with differential graded algebras and to hide all the complexity into the differential of an algebra, namely to consider multiplicative free resolutions. One can work with algebras by hiding their complexity in multiplicative free resolutions. What do I mean by that? I mean a multiplicative free resolution. So suppose that A is an algebra. A multiplicative free resolution of A is an differential graded algebra which is free as an algebra, and has A as its homology. So it's an you take a graded vector space V, and you consider you equip it the free algebra generated by V by with an element delta, D, sorry, which is an element of degree -1 with respect to the degree of V. I don't think about the degree of words in V, so the only thing that matters is the degree that comes, somehow internal homological degree of the vector space V. Of D of degree -1, D squares to 0, so we can talk about homology of D, and D is a derivation, a graded derivation, so D of AB is equal to D of AB plus -1 to the power of the degree of A D of B. Then the homology of this differential on the free algebra is also an algebra, and the requirement is that this algebra is concentrated in degree 0 and is isomorphic to A. So somehow what happens is that your original algebra A was generated by some elements. Now this space of generators V will be much bigger. It will usually be absolutely gigantic. But the algebra structure will be very simple. It will be a free algebra, and all the complexity will be hidden in this differential D. Now, how to I am ready to introduce another slogan here. So that suppose that our goal was let me write a slogan, then perhaps explain it. So the slogan is that the deformations of an algebra with monomial relations are in one-to-one correspondence with perturbations of the differential in a multiplicative free resolution of such an algebra. And what I mean by perturbations of the differential is the following. So, okay, so we want a multiplicative free resolution of the algebra A. Somehow, okay, I told you that V is a graded vector space, so it has components in degree 0, 1, 2, and so on. Okay, elements of degree 0, they generate the homology in degree 0. So let us assume, for simplicity, let us work with the V that starts with X with generators of A living in degree 0. Then somehow in the algebra generated by V, you have the free algebra generated by X. And of course, you want to impose the relations, which will appear after you compute homology. Somehow this means that you want to place your relations in homological degree 1. So somehow, so that the images of these elements will create, under the differential, will create you the honest relations. And then there will be some other things. This would be true for the monomial, for the honest algebra A. For the monomial algebra, you have to put here the leading terms. Now, if you, so this will create you something like this, and if you now, so here the differential just maps each such element to the honest leading term. And this creates at least the correct homology in degree 0. Now you can perturb this part of the differential and map it not to the honest leading term m, but to the relation m minus f of m. So add some lower terms. And so this slogan means that deformations of an algebra with monomial relations are in one-to-one correspondence with coherently perturbing all the other bits of the differential by adding some lower terms, which would then create the property d squared equals to 0 and create the correct homology. Now, so yeah, if it is the if your intuition comes from non-differential graded algebra, then of course that might look as a bit of an overkill and a bit mysterious, but somehow that is so, and perhaps some insight that will people who work with, for example, with commutative algebra and with Lie algebras in the context of Lie superalgebras in the context of rational homotopy theory, they do more or less the same on a regular basis. It somehow relates to two equivalent approaches to doing algebraic topology with rational coefficients, going back to Quillen and to Sullivan. And so this is just an analog of what rational homotopy theory does in the case of non-commutative associative algebras. Now, we're getting very close to the second part of the title of my talk, the Maurer-Cartan equation. So somehow, in general, the Maurer-Cartan equation is an equation. It happens generally in a differential graded Lie algebra. So a Lie algebra equipped with a graded Lie algebra equipped with a graded derivation that squares to 0. And this Maurer-Cartan equation, it's an equation, let me denote Lie algebra L. It's an equation for an element x of homological degree -1, and it says dx plus 1/2 bracket of x and x is equal to 0. So since we're working in a homologically graded Lie algebra, you use the superalgebra signs. So the bracket of x and with itself for an element of degree -1 is non-trivial, and so this is this equation is called the Maurer-Cartan equation. It goes back to work of Maurer and Cartan on differential geometry, where it is the equation of flat connection. And then somehow it appears in many different situations. It appears in deformation theory. It appears in mathematical physics as the master equation of Battalion and Vilkavisky. It it appears in it appears in algebraic topology. It appears in some ways directly and indirectly in some representation theory. There are many different situations where this equation appears, and somehow the in homotopy algebra, so where my intuition is coming from, one reason to write this, one very important class of differential graded Lie algebras that one works with where one studies this equation are the deformation complexes of algebras. And so, as I was telling you, so if you have an algebra A, one can hide the complexity of this algebra in a multiplicative free resolution, which let me call F, which what I previously denoted by this. And the differential graded Lie algebra that one can construct out of such multiplicative free resolution is just the derivations. Well, the graded derivations, of course. So it's a Lie superalgebra of graded derivations of F, of the multiplicative resolutions F. And it turns out that the Maurer-Cartan equation, so it has a differential coming from the differential of the resolution. And the Maurer-Cartan equation in this algebra precisely describes perturbations of the differential. And so somehow this is so far another reformulation. So we started with talking about confluence. We interpreted confluence as the fact that algebra A is a deformation of the corresponding algebra with monomial relations. Then we, to study deformations, we study perturbations over multiplicative free resolution of the algebra, a resolution F of the algebra with monomial relations. And so now we want to study the Maurer-Cartan equation in the Lie superalgebra of derivations of the multiplicative free resolution. Now, the point somehow, well, I mean, perhaps I should say, this is what I want to say. And somehow the point, the reason why diamond lemma, which I haven't yet stated, is so powerful is that it gives a very specific and sometimes not so big set of conditions to verify. So now I am going to tell you, to start telling you what the diamond lemma is. So the diamond lemma says that you have to look at all possible monomials that are divisible by two different leading terms which overlap like this, more or less. Such an overlapping monomial you can rewrite in two different ways. You can rewrite this leading term, or you can rewrite this leading term. So there are two different ways to rewrite. So what Diamond Lemma says is that as long as those two different ways can be themselves rewritten to something common, for every overlap like that, then you have confluence. And of course, in fact, it's the if and only if condition. So you just need to look at how the leading monomials that you want to rewrite overlap with each other, and then just do rewriting and see if you end up in the same place. So it's something that you can teach a computer to do. But I want to emphasize that it's not only, of course, a computational tool, it also can be used to prove some theoretical results. So Diamond Lemma, Composition-Diamond Lemma, it's an amazing, very powerful result. So my goal now is to explain to you in the last few minutes how to interpret this picture from the point of view of perturbation of the differential, the Maurer-Cartan equation. So somehow, since we're talking perturbations of differential, I didn't write the word differential here. Since we have a differential which is derivation, a differential is a map from the space of generators into the whole free algebra. And then you extend it by the derivation property. So you have V0, V1, V2, and so on. On V0, differential maps to 0 because there are no elements of negative degrees. So here there is no room for perturbation. V1, perturbation of differential on V1. It's precisely replacing monomial relations by some non-monomial relations, throwing in some leading terms. So perturbation of V1 is something that you are given and you want to test if this rewriting system is confident. So somehow the general philosophy of the Diamond Lemma is in fact equivalent to saying that you just need to check that everything is okay on generators of degree 2. And this is precisely our main observation, which I believe is new, even though it's a very simple one. Main observation. The differential of our multiplicative free resolution deforms if and only if it deforms up to homological degree 2. So somehow you need to check some conditions, that everything is coherent in homological degree 2, and then on generators of higher homological degrees, everything will happen absolutely for free. So it's and it has an equivalent formulation in the language of the Maurer-Cartan equation, which is in fact how we prove it in our paper, because the language of the Maurer-Cartan equation permits for doing some simple calculations in differential graded Lie algebra instead of doing instead of thinking about multiplicative free resolutions and so on. So somehow this observation, by the way, if you allow me some informal remark, relates to famous quote attributed to Gelfand, who somehow was saying that homology and cohomology, it's like doing homology. Cohomology is like doing differential calculus. So the first homology is velocity, like velocity. The second is like acceleration, and higher don't really make much of sense in the real world. So somehow this phenomenon that we observed corresponds precisely to this philosophy, that once you deform the differential up to homological degree 2, everything else happens absolutely automatically and doesn't carry any extra information relevant for the real world, where you have really interesting algebras you want to work with. And finally, what I want to say is that how to recover from this, how to recover the classical diamond lemma. Somehow, and also what happens for different choices of the multiplicative resolution F. So I will answer these two questions more or less simultaneously. So first of all, there is one particular choice of F. I remind you that F is a multiplicative resolution for monomial relations. One particular choice of F, which was found by myself and Anton Haroshkin about 10 years ago, which we call the inclusion-exclusion resolution. I don't have time probably to define it, so I will just tell you that such a resolution exists, which recovers directly, the condition of the composition-diamond lemma of Bokutz and Bergman. So somehow, in fact, so the space V of generators of the inclusion resolution is formed by all possible overlaps of the monomial relations. So the combinatorics is precisely right. And in homological degree 2, you just have overlaps of two monomials. So everything works perfectly fine. And another useful choice of F, you can take the what is called the minimal resolution, multiplicative resolution. And this was computed for monomial algebras by Pedro Tamaroff in 2018. And for the minimal resolution, you get a slight optimization of the composition-diamond lemma, which somehow says that you can focus only on some overlaps which are essential, and everything else you get absolutely for free. And this is related to what some people call the triangle lemma in the context of associative algebras, which this name, I believe, is due to triangle lemma is due to Viktor Latyshev, and in the commutative case, it's related to what is called Buchberger's second criterion. So it's some optimization which says that you don't really need to check all overlaps, but only some overlaps. So somehow homotopy theory also knows how to optimize verifying confluence, namely you optimize it by taking the minimal resolution. Somehow within a 1 hour talk, this is more or less as much as I wanted to tell you. I'll just take 1 more minute to say that the way it is done, as I said, it's very suggestive, meaning that you can use the same methods to either recover known diamond lemmas for other types of algebras, not necessarily associative, and to guess new diamond lemmas for various types of algebras where the corresponding result is not necessarily known. And the general philosophy always is that the diamond lemmas come from multiplicative free resolutions of algebras with monomial relations, no matter what kind of algebras you consider. I think that it's a good moment to stop, so I will stop here and thank you for your patience.
Okay, let us thanks. Questions, comments?
Okay, Volodya, I have the following question. It's Leonia Makarimanov. Can you, on this language, interpret the following? Suppose you have an ideal which is principal ideal given by one element.
All right.
Can you, with this technology, discover that canonical forms, standard forms for elements, are not all zeros?
That is a great question, and somehow, sadly, as stated, the answer is no, because from the point of view of applying various results to a particular algebra, usually what I am telling you about doesn't have more insight than the existing diamond lemma of Bockut and Bergman. So it is rather a way to reformulate the diamond lemma in a way to make it more adaptable to other algebraic structures and to understand where the confluence condition is conceptually coming from. But if it so happens that for a specific algebra you have some nice multiplicative free resolution, then sometimes it can help something. But in general, it probably wouldn't.
Too bad. Okay. It's true in zero characteristic, we still don't know it in finite characteristic.
Алгебра ассоциативная с одним соотношением, это же открытая проблема, разрешима там или нет. Это, если бы тут было...
Валюта.
Да. Okay, more questions, comments?
may I have an announcement?
Yes, yes, yes.
Okay,
Okay.
tomorrow, one of the persons who participate in the seminar now, this is Vava Kushvukova, will have a talk in Sofia. You can see in the chat the title, the name, and if you go to the homepage of the institute, you can see information about the Zoom session, how to enter there.
But it's still in some ungodly hour, right? From our point of view.
Early, in Sao Paulo, it's 11 in the morning. London is 2 p.m., in Sofia is 4 p.m. We moved especially to be convenient for the people who are like you,
Yeah.
speaker.
Okay.
Okay. More questions, comments, announcements?
Okay. Let's keep. Oh, yeah.
Okay. Let's thanks again, Vladimir. Very interesting. Very. Спасибо, Володя.
Thank you. Thank you.
Goodbye.
And I want to make an announcement for the next Thursday. The next Thursday we will have a speaker, Alexander Zubkov, and he will speak of Harishchandra pairs and group superschemes. How to say? Harishchandra pairs and group superschemes. Alexander Zubkov. The next Thursday at the same time. So everybody is welcome. And now, okay, that's all for today. Thank everybody for attention, for coming. Till the next Thursday. Bye-bye.
Bye-bye.
Goodbye.